Oh, there he is. Yeah, what I thought I would do on this session, because we do have a little bit of time, Monday we'll probably do chapter 8 and get into chapter 9. And then Thursday we'll do 10 and 11. And then Friday morning of next week, we'll go ahead and do a review of everything, you know, sort of a pre-examination review. And I just sent out an email to everybody, essentially reiterating what some people have asked directly, which is there are essentially 3 components to taking the certification or getting the certification. One is completing the education, which we're doing through this class. A second is doing the hands-on labs. And the third is passing the examination. Now, they don't have to be done in any particular order. You know, logically, you'd want to take the class before you take the exam, I hope. But basically, you will not get the certification until all 3 are completed. So if you want to take the examination prior to taking the hands-on labs, then you can do so. You know, the labs will be next Saturday and Sunday. We're going to do the review Friday morning, so you might want to schedule your exam for Friday afternoon if you're going to do it remotely, because everything will be fresh in your mind and it just might be a better time for you. That's if you're using the remote proctoring option. There is a 3-day advance period for registering for that. So if you're going to do the remote proctoring, get that process underway. Pick the time you want to take it and go ahead and fill out the registration form. It's at the ETA website, and get that all taken care of so everything's scheduled in plenty of time. And there's a $14 fee on that advanced proctor or the online proctoring. That goes to the proctoring organization.
How will they have known that we've already paid for the exam?
Yeah, what I'll do is I'll go ahead and send a list to ETA and let them know the names of everybody in this class. And what they do, when you're signing on there, if you just say University of Dayton, or just say Blue Rock Station under the purchase order, and they'll know it's me. Let's see. To ETA. Okay. So yeah, you won't have to prepay for your exam, but you will need to pay that $14 to the exam room AI, which is the proctor. Now we are going to give a pencil and paper exam on Saturday. So Saturday, I think that's October 10th. So we're going to do the hands-on labs. One half of the group will be there from 9 until, probably take until about 4. And then as soon as we're done with the labs, we'll go ahead and sit down and take the exam. So if people would prefer to take the hands-on or the exam using just a Scantron sheet and pencil and exam booklet, we'll do that Saturday evening. So if you're going to do the hands-on labs on Sunday, if you're coming in from out of town or whatever, you can come in, do the exam, then come back Sunday morning. Or if you're doing the hands-on Saturday, you'll do that and then take the exam. So that's an option. Now, one thing that is not an option is to sit for the online exam, fail it, and then hope that you can come in on Saturday and take it again. You can retake the exam, but you have to wait 30 days between attempts. I guess they figure that you might memorize all the questions or whatever, and just sort of do it by rote. So hopefully nobody's going to be failing the test, but that's not going to be an option to take the remote one on Friday and then hope you can sit for the paper one on Saturday, because that'll just be too tight, too close. Okay. Any questions on that process at all? I'll be sending a note to everybody with the list that I have on who's going to be taking the hands-on on Saturday, who's going to be taking it on Sunday. I still haven't heard from one individual, so hopefully we'll get everybody sorted there. Okay, so then what I thought I'd do here today is try and walk through a specific problem, like if we're gonna do a design for a home. So does anybody want to volunteer their home as an example? We can design a PV system for your house.
Sure.
Sure, Corey? Okay, so Corey, what is your address?
The whole address or just the town?
No, the whole address. I'm gonna pull you up on Google Earth and we're gonna look at your house.
It's 140 Ridgecrest Road.
Okay, what city?
Wheeling, West Virginia.
All right, okay, I'm gonna jump in here, going to Google Earth. All right, so you said it's 140. Is Ridgecrest just one word?
Yes.
There you are. Wheeling, West Virginia. Okay, we're zooming down. And this is a tool, of course, that you'll use quite a lot. It's making me dizzy. All right, does that look like your house here?
Yeah.
That's it? Okay, so,
Yeah.
all right, so you actually, it looks like you've got one shade tree in the backyard. Or is that's, how is this? Is this your house and your frontage is to this road? Or is it?
Yeah,
this-
the house faces the road.
Okay. So this one, your house faces west or east, sorry?
No, it faces west.
Okay. Trying to get my orientation here because it looks like this would be south.
No, that's north.
Oh, okay, that's weird. Okay, let's get that oriented. There we go. Now we're north-south. Okay, so south is what we're looking at right here. And this is the tree here. So you have a couple of options. It looks like there's a fair amount of roof space here on the south exposure, although it looks like it's a fairly complex pitch on your roofs. It's not a straight design. You've got some peaks and dormers and things like that. Is that right?
Yeah.
Okay, so we may want to, if I were going to recommend here, does your property go all the way back to these trees here?
No.
Do you end right here on your pavement kind of thing?
It comes down to about the edge of that little basketball court right there.
Okay, that's what the arrow is on. Can you see the arrow?
No, that's the driveway.
Okay, so, this is the basketball court here.
Yeah.
Oh, okay. All right, so you have an option if you wanted to do a ground mounted system. It looks like you've got plenty of space. You could either do a carport, to park your cars under if you wanted to,
Mhm.
or you could just go out here in the lawn and put a ground mounted system. I guess if I were consulting on this, I would recommend that because you have no obstructions over here. This tree won't be a factor because it's north of where you're going to be putting the array. And so you could really put an array right in this square right here. And depending on how far, you'd have to look at your setbacks requirements from the property line. Or you could put a canopy type array right in here. So it just looks to me like your roof is going to be too difficult. And I always like to avoid putting arrays on roofs if I can, because you're messing with the roof at that point. If you have space for a ground mounted system, it's always a lot easier. And you usually cannot put them in the front yard. There's usually deed restrictions or whatever for that. So the backyard is going to be the place for it. So as the homeowner, is this acceptable to you?
Sure.
All right, sure. It's all theoretical. Who cares, right? Okay, so we'll figure we're going to do a ground mounted system. Now what we have to do is figure out what size array are we needing. So because this is an existing home, the load assessment would typically be, let's look at your utility bill. And I don't know if you happen to know offhand what your average utility usage is. Do you know?
I did it. It's about 8,000.
8,000?
Well, wait. Yeah. I worked it out. It's about an 8,000 array is what you would need.
Oh, okay. Well, yeah, but let's do it all the way. So what would be your month? Let's just assume, was your consumption above average when you looked at it?
Not really. No.
So we know that the average suburban American home will use about 900 to 950 kilowatt hours per month. Okay, that would mean in your part of the world, probably you're getting an electric bill in the neighborhood of between 100 and 125 bucks a month. Does that sound about right?
Yeah, that's about right.
Yep. So let's just
Yep.
let's just assume you use 1,100 kilowatt hours per month. Okay. So let's go ahead and go to the whiteboard here. And we'll just start figuring out what size array you need. So if we start with 1,100 kilowatt hours per month, what's the first step that we do? We need to get to the daily load, right? So we're going to divide that by about 30.5 days per month. And we get anybody doing the math?
$36.
36 kilowatt hours.
Yeah. 36.1.
All right. So that would be kilowatt hours per day. All right. So what's our next step? We need to get this from kilowatt hours per day to kilowatts.
Need hours of installation.
Right. So what we would do is we would go to PV watts. And we would look up Wheeling, West Virginia. Okay. And we know that we can set the orientation exactly in a ground mounted system, right? So we can go 180 degrees true south because our roof pitch is not an issue. And we also know, or I know from experience, anywhere between say 26 and 34 is going to give me the right, the optimal in this part of the world. So I'm going to put the tilt at 30 degrees because that's right in the sweet spot area. And now I need to see what is the insulation. And the insulation is going to be 4.59 hours on average, or 5.8. So that's going to be our insulation. So I'm going to divide this 36 by 4.58. That's going to be hours per day. So the hours per day cancel. And what's 36.1 divided by 4.58?
6.63.
6.63. So if this system were 100% efficient, then you would need a 6.63 kW array. But we do know that this system is not going to be 100% efficient. So why don't we, just for giggles, I would probably do either a power optimizer system, probably a power optimizer, but maybe a microinverter system. But because I want to practice string calculations, let's pick a string inverter. So we need to go in here. It's going to be a grid-tied system. And we're going to need to find a string inverter that's in the neighborhood of 7 kW or so. So I'm going to pick this Fronius 7600 watt inverter. Okay. So that's going to cost you $2,000, right? It's a 7600 watt. And a couple of the things that I need to find out from this inverter is what is its operating range, its minimum voltage and its maximum. And that is going to be 80 volts is minimum, 600 volts is maximum. And then I want to find out what is its efficiency. Well, its best case efficiency is looking to be about 96.9%. So I think I'll just count that as 96% because it's not going to be maximum efficient all the time. So I'm going to need that for my D-rate factor. All right. So I think that's all that I need for my inverter at the moment. So if we go back to our calculations, for inefficiency, let's just say our D rate, we're going to say 2% voltage drop and 4% inverter. And then we're going to put some module level power electronics. Or tell you what, let's not do that because it's a ground mounted system. We don't need to have any kind of rapid shutdown provision here, but I'll just show you what that impacts. Because the panel that we're going to select, let's just assume it has a plus or minus 4%. So some panels work 4% better than others. Well, because we're putting them in a string, that means that there is going to be a minus 4%. Because everything's going to operate from the lowest common denominator. And then I'm going to throw in, for connections and miscellaneous, another 2%. That's probably all I need to do on my D rate. So at this point, I'm D-rating it by 12%. Okay, so now I divide this by 0.88 and we get what? This is my D rate.
$7.53.
7.53 kW. So that 7.6 kW inverter that I picked is going to do pretty well for us. It's certainly adequate. Because of clipping, we don't have to match them exactly, but it's nice. It's nice if it's not going to cost me a lot of money. So I'm not going to clip off any. So this is the size of the array. So this is how we determine the size of your array. Now what we're going to do is we're going to go and we're going to select a panel. So if we want to select a panel, I'm going to assume, Corey, that you're cheap, right? So we'll pick one based on price. Okay, and this nice thing with this Alti website is you can sort these by price per watt. So the cheapest one that they've got is an REC Solar Twin Peak 375 watt monocrystalline, 45 cents a watt for that panel. So that's a pretty good price. So let's just go ahead, just randomly, we'll select this one. So it's going to be 375 watts per panel. And it's, so now I'm going to need to find out a few things from this solar panel. In the spec sheet, it's going to tell me, we're going to go with this column here. So the VOC is going to be 47.4 volts. The VMP is going to be 40.1. The ISC is 10.04 amps. And the IMP is 9.36 amps. Now, I'm also going to need to know the temperature coefficient at VOC and VMP, and that usually is a little harder to find. You got to go to the data sheet typically. And this data sheet here, when it catches up, come on. There we go. Temperature ratings, they're down here. So the temperature coefficient at VOC is 0.28% per degree Celsius. 0.28% per degree Celsius. And the temperature coefficient at Pmax, which would be the VMP, is 0.37% per degree Celsius. And I wonder if we can find here, if it tells me what its plus or minus would be. I don't want to search around very much, but often in these spec sheets, it'll tell you what the, you know, how much variance we would expect between panels. Yeah, let's not search for it. It's got a 25-year warranty. Pardon?
Is it at the nominal operating cell temperature there? It says plus or minus 2 degrees C.
Plus or minus. No, that's not where we're getting. That's a different issue. I was just looking, I forget the term that they use on it. It's like the power factor or something like that. Anyway, it's not worth searching on at the moment. Okay, so we go back to our calculations. Well, the first thing we might want to know is how many panels. So we know this is the size of our array. They're 375 watts each panel. So how many panels are we going to need? So it'd be 7,530 divided by 375.
Looks like 20.08.
20.08. So that's close enough to 20 for me. You know, we'll round it down just a wee bit. So this is going to be the number of panels. Now we may have to do some adjusting here in a bit, but that's where we're going to be coming from here. Now let's assume that we're going to be doing this as a string. We could look at our inverter, and chances are these modern inverters, we could run everything direct into the inverter. So we could run 2 strings all the way, but I want to do this with a combiner box. I don't want to run all those circuits all the way from your backyard to your house. I want to run them and combine them at the array. So at this point, we're going to need to know what are the maximum number of panels in a string and what's the minimum. So what do we need to know before we can determine what the maximum number of panels are in the string?
The hottest temperature ever recorded.
That's right. So we just go
Trying
in.
to find it.
So hopefully it'll say Hottest day of the year. Sometimes it's not all that easy. I moved that out of the way. Annual temperature and extremes. The hottest temperature ever recorded was 112 degrees Fahrenheit. And while we're at it, the coldest temperature ever was minus 37. Okay, but we
How
need
did that for
Celsius.
all of West Virginia?
Pardon?
It looks like that might be for all of West Virginia. Does that matter?
Yeah, it's close enough. Martinsburg, yeah, it'll be close enough. Then, so then you'll just use an online conversion here. So what's 112? Gives me 44.44. Or 44 degrees Celsius is probably good enough. And 37. Whoops. So minus 38. All right, so we've got our hottest and our coldest in Celsius now. So we're going to jump in and move everybody's pictures over. Okay, so with the, is it okay if I get rid of this, what I've got here so far? I'm going to write down that we need 20 panels. And they're 375s. It's a 7.53 watt. And the inverter is 80 to 600 volts. Of course, I did that before I won't be able to just do an erase screen. All right. It's like working with a real chalkboard. Okay, so we do the temperature. Basically, we take for the longest, it's going to be minus 38 degrees. We take the coldest temperature, the difference, 25 degrees Celsius, which is STC. And we're looking for the delta between those two. So it's going to be, what, 63? Is that right?
Yep.
All right, so the delta is 63 degrees, and we know that the temperature coefficient at VOC was 0.28% per degree Celsius. So we multiply 0.28 times 63, and we get what number?
17.64.
17.64%. So we know on the coldest day ever experienced in Wheeling, West Virginia, that panel is going to produce 17.64% more volts. Well, the VOC, which is the worst case voltage or the best case, depending on how you want to look at it, was 47.4 volts times 117.64%. Or we could decimalize that as 1.1764. And we end up with
55.76.
55.76 volts. So every panel now, the panels we've selected, could theoretically produce 55.76 volts on the coldest day ever. We look at the maximum threshold for our inverter, and in that case, it's going to be 600 volts divided by 55.76, and that's going to be 10 or 11, right?
Yep, 10.7.
10.7, round down, 10 panels max. Okay. Everybody see how we do that string calculation there? Okay, so now what we're going to do is figure out the minimums. And the minimum is going to be what's the delta between the hottest temperature ever, which was 44, and standard test conditions. It's going to give us a delta of 19, is that right? But because this is a ground-mounted system and the temperature of the cells are going to be different than ambient air, we add 25 degrees Celsius back to it because it's a ground-mounted system. Had it been a ballasted system on the roof, we would have added 30 degrees. And if it were a flush-to-roof mounted system where it's about 6 inches off the deck, we would have added 35 degrees. So these terms, these numbers come from ASHRAE, the heating and air conditioning guys. So this is just compensating for the fact that it's hotter there than the ambient air temperature. So at this point, we're back to a delta of 44 degrees, right? Because we subtracted 25 for STC and we added 25 back in because of ground mounted. So our delta is 44. Now we're going to multiply that times the temperature coefficient at VMP, because we don't want to go air on the high side, which was VOC. Now, because we're talking about the minimum, we're going to do it at what the operating or the VMP would be. And that's going to be 0.37% per degree Celsius. So what's 44 times 0.37?
16.28.
Yep, so 16.28%, but that's going to be less. So on the hottest day ever, that panel is going to produce that much less. So now again, we're dealing with the VMP, not the VOC. So I'm going to take 40.1 volts, which is the VMP of that panel, times 100% minus 16.28%, or 0.8372, is that right? 83.72%.
Yeah.
So how many volts is that? It's going to be around 33, 34.
Yeah, 33.5.
Where is it? No. I think you went the wrong direction.
How so? We're talking about the hottest day of the year, so the panel will actually produce less voltage.
Oh, times it. Okay.
Yeah. So it should logically be producing less voltage. And on the coldest day, it should logically be producing more voltage than what it's rated for. So now we know that on the hottest day, that panel is going to produce 33.5 volts. We look at what is the minimum amount of voltage that inverter needs to start up, and that's 80 volts, 33.5 volts. So we're going to need 3 panels minimum, right? It's going to be 2 point something. Everybody see that? Okay, so on the hottest day ever, we need at least 3. On the coldest day ever, we can't have more than 10. So we do need 20 panels total. So this one looks like a pretty clear-cut case of 2 strings of 10. Everybody see how you would configure it? 2 strings of 10?
Mm-hmm.
All right, so at this point, let's just draw out what the system is. We've got this, and it was, and I erased it, but it's, what's 20 times 375?
7,500.
Okay, so it's a 7.5 kW array. We've got 2 strings 2 strings, 10, coming into a combiner box. Okay, and now from here, I want to go and I want to go to a DC disconnect that's going to be located at their home. And that DC disconnect has to be within 10 feet of the inverter. So this distance here to here can't be more than 10 feet. All right, so if I were going to put overcurrent protection in here, let's say a breaker, and in this case, because this is going to be a transformerless inverter, we're probably going to need breakers on both the positive and the negative wires. So there'll basically be 4 breakers in this DC disconnect or in this combiner box. And each of those breakers, well, what would it be rated for? The ISC is, or sorry, for breakers, we would use the IMP, the actual. So 9.63 is your ampacity. So each of your strings are going to be, the amps could be times 1.25 times 1.25. So 9.63 times 1.25 times 1.25 is what?
Uh, 15.04.
Yeah, 15.04. Or close enough to 15. So I'm going to say 15 amp breakers. So you're going to need 4 of them. Now, what size wire are you going to have in there? Well, in that case, we would figure it based on the ISC, which is going to be 10.04 times 1.25 times 1.25. Because for wire size, we're always figuring the maximum. And the ISC is the theoretical maximum amperage. So I get 15.69 or so. Is that right?
Yeah.
Okay, so notice with the PV source circuit, it's always going to be those wires that are connected to the panels, and those are 12 gauge. So I don't really have a table here, but do any of you guys have the table for ampacity available to look up what 12 gauge amp rating would be?
It's 25, right?
25, that sounds right. 25 amps max. So that's certainly well within what we're needing. We're saying worst case, it's going to be just under 16. The wire that comes pre-wired is rated for 25. All right, so now we're coming into a combiner box and we're going to combine them. Well, the combined ampacity, because we're making a parallel connection, there are 2 strings. So now we're going to be dealing with 31.38, is it, amps? So what's the ampacity rating for 10 gauge wire if we read from column 1?
I don't know. Is it
Somebody have the
55? Is it 55?
no, that'd be 6 gauge wire. 10 gauge
Oh, right.
wire.
40?
Read from column 1.
I don't have it up.
Jay, while we're talking about that,
Yeah.
How does your voltage play into this? I mean, we've always talked about how increasing your voltage reduces your wire size, but here we're talking about amps and 12 gauge wire and 10 gauge wire. When does it come into play that if you increase your voltage, your wire gets smaller?
Yeah, well, in this case, it is automatically because we set these strings at 10, which was pushing it up around
Okay.
pretty close to 600 volts.
So you're getting your
Yeah, I was trying to make my
maximum voltage right now. So you got
Yeah, we're doing the maximum
All right.
voltage allowed. Now, we could have done 10 strings of 2, at which point the ampacity would be basically we'd do the 15, or we'd have this times 10 or 160 amps. Well, then you'd be talking about 4-aught wire coming from here to
Got
here.
it. Okay.
So
All right. That makes sense. All right. Thank you.
10 is 30 amps.
30 amps. And what
Yeah.
is 8 gauge wire? Is that
40.
all right? So in this scenario, we'd probably, because we're at 31.38, we'd have to go with 8 gauge wire, right? Because 30 just isn't enough because it's 31 point something. So the inspector would require that we have 8 gauge wire going from here to here to this DC disconnect. Okay. Now, what would be the ampacity rating of the DC disconnect? Well, if they come in 30, 60, or 100 amp boxes, we would probably put a 60 amp DC disconnect in there. And if it were fused, you could put a 30 amp fuse in because we got a lot of safety margin in here, but you might want to put a 35 amp fuse in there. And then the wire gauge between the DC disconnect is just, a place to open or close. So the ampacity doesn't change. So this would still be 8 gauge. The ampacity would still be 31.38. Okay, so this would be how we'd size the wire going here. Now from the inverter to the AC disconnect, what size wire would we have? Well, we already said this is a 7.6 kW inverter. That was the size that we selected. So we have all of the information you need to determine the wire size. What wire size would it be? Well, watts equals amps times volts, right? And we're trying to figure out amps. So what is the voltage
It
coming
would
from our
be-
inverter?
You would need a number 6 gauge. Number
Okay.
6.
All right, well, that might be right, but let's double check. How'd we get that?
I think I added the solar variability, but you're not supposed to, right?
No, you're not supposed to because that's no longer a factor. So we take the maximum wattage coming from the inverter, not the array, but the inverter. We divide it by 240 volts, which is the voltage output of the array or of the inverter. And what is our amps?
Is it 30?
Is that right?
31.6.
Is it really? It's going to be pretty much the same, huh? 31.6
Yeah.
amps. And then we
Yeah.
multiply that times 1.25, which is the NEC safety factor. We have to do that all the time. So 31.6 times 1.25.
39.58.
39.58 amps. So we can still use our 8 gauge wire, right?
Yeah.
No worries. So we're still just using the same roll of wire we bought down at Home Depot or whatever. And now what size disconnect are we going to need? Well, 40 amp. So it's going to be a 60 amp disconnect. If we wanted to put a fuse or a breaker in there, it would be probably a 40 amp breaker. Now we're going to come in and we're going to hook into our service panel. Going to go into we're going to do a load side connection. This is the meter. So what size double pole breaker would we hook in?
40 amp.
40 amp, exactly. Now, is this permissible? It would only be permissible if this box is rated for 200 amps. If we have a 200 amp service coming in, we're still fine. We're within the 120. And this is fairly common to have 200 amp service coming into a 200 amp box. So this 40 amp breaker will work just fine. And we want to locate that as far away from the main breaker as is physically possible in the box. Okay, so that's everything that's involved in designing your system, but we have one more equation to work through, which is our voltage drop equation, right? Just to see if our D rate of 2% is adequate. So what we would have to do is this is usually, the PV output circuit is usually the problem child in these things, because that's the one that's going to be going from your array to your home. And in your case there, Corey, this thing was in your backyard, so it might be, let's just say 80 feet. So this run is 80 feet. We said this couldn't be any more than 10 feet. From here to here, probably another, I don't know, 10 feet or 15 feet. And this one might be 15 feet. So if we want to figure out our voltage drop, well, it's kind of, it's easy because it's all going to be 8 gauge wire. So we can just simply add up 80 feet, 10 feet, and then 15 feet and 15 feet. And we're going to get
120.
120. So our distance is going to be 120. The voltage drop equation is voltage drop equals amps times resistance times twice the distance over 1,000 feet. Well, what are the amps? Now we don't have any safety factors in here. So the amps are going to be 9.63, which is your IMP, times 2, because we're hooking up 2 strings together. So that's going to be 19.26, is that right?
Yeah.
So 19.26 amps. We know the distance is 120 feet, so that's going to be 240 divided by 1,000, or 0.24. So now the question is, what's the resistance? So we look up in that resistance table. I don't remember which page it's on. I think it's page 69 or somewhere in that range. And we want to see what is the resistance for 8 gauge stranded copper cable.
.778.
Okay, and that's going to be ohms. So what's 19.26 times 0.778 times 0.24?
Times 240? Is it 240?
Now I get 3.6. .24. So it's 19.26 times,
3.5.
yeah, 3.5962, or close enough to 3.6 volts. Okay, so what percentage of our system voltage is that? Well, we know that we're hooking up 10 panels in a string. And we also know that the VMP is 40.1. So this system, excuse me, is going to be operating at 401 volts DC under standard test conditions. Right? So our voltage, our standard test conditions, 400 volts. We're going to lose 3.6. So actually our voltage drop is going to be a little less than 1%, right?
Yeah, I got 0.89.
Yeah, so 401 volts divided by 3.6 volts. You said it's 0.889? So that's the
That's what I got.
percentage. Well, we had allocated 2% in our D rate factor, so we're in good shape. The voltage drop will not be an issue. And just as a rule of thumb, unless these numbers are over 200 feet, the voltage drop usually isn't going to be an issue as long as you've sized wire big enough to handle the amps of your system. All right, so I guess the main takeaway here, to me anyway, is every step here is pretty straightforward, pretty easy. It's just that there's so many things to remember that it's easy to get tripped up. So it's not like we're doing trigonometry or complex mathematics. It's just that there are a lot of factors that you have to kind of play with. And these systems really lend themselves to spreadsheets, you know, because all you do is you just fill in the blanks. And so there are a lot of automated techniques of doing this where you just plug in what is the VOC, what is the IMP, what are the distances. You're just plugging in raw numbers and out spits the answer. But I want you guys to do it this way because I want you to understand what's going into those answers. I've had some students who do design work of solar and they don't understand what they're doing. They're just plugging numbers into computer programs and getting an answer. So they don't know if it's right or it's wrong. So.
What would change if the power went on the supply side rather than to the panel?
Oh, what would change here? Yeah, well, what we would find, for instance, is basically a supply side connection would look something like this. I need actually to get the right tool. All right, so here's our service panel box. And instead of hooking into the service panel, we would hook in somewhere between the meter and the main. That would be what's referred to as a supply side connection. And you'd have to hire an electrician, come disconnect your service from the electric company up at the transformer at the meter. They'd have to come in and cut the wire, put in a junction box, and then have a place where you can make a connection, a tap into that, into the wire. Now, the question would be, what size wire do we need for this between the AC disconnect and the wire here? Well, for a supply side connection, there is a rule that says at minimum, it must be 60 amp. It must be rated for 60 amp. And the AC disconnect must be rated for 60 amp. So right off the bat, that's your minimum. That's your base. Now what we would have to do is figure out what is the actual ampacity here. Well, you've got 200 amps of service coming in from the array or from the grid. But you're not going to have 200 amps flowing through this wire unless for some reason there's a ground fault that takes all that power and throws it down into the ground, because nothing over here is going to draw 200 amps, right? Your system is only going to be you know, it's a 7.6, so we're only talking 30 some amps maximum over here. But you could have a fault where all the power wants to rush through this line. So at that point, you're going to want to put some sort of fuse or something in this AC disconnect. So if there is a problem, it stops at your AC disconnect. You're not going to damage any of your equipment further on down the line. Let's say a squirrel comes and chews a wire and causes a ground fault. You don't want all the power rushing in from the utility through here and frying all of your electronics. So you want to have some sort of overcurrent protection device at the closest point, which is going to be your AC disconnect. Now, I can't really tell you what size wire is, because now it depends on, is this 10 feet? Is it less than 10 feet between the AC disconnect and your tap? Or is it less than 20 feet, or 25 feet, but greater than 10 feet? It cannot be more than 25 feet. That distance cannot be more than 25 feet. But there are two different formulas that you would use. One if it's the 25-foot tap rule, and one if it's the 10-foot tap rule. And I don't remember what those are off the top of my head. So I'd have to look them up in the book to calculate it, but it's pretty straightforward. Once you know
So
what.
Jay, what's the advantage of supply side versus load side?
Well, there can be multiple advantages. One is, let's say that your service panel is full. You just have no spots in it to connect to. Well, your only
Okay.
option would be to have an electrician come and trade out your service panel with a bigger one or a better one. And that usually is going to cost you like $2,000. So you want to avoid that expense. There may be another situation where going through the building might be very difficult. Let's say it's a historic house, you know, that you don't want to drill through the wall, or it could be a great huge stone house. Trying to get into the building might be difficult. So you can make this connection and you can keep everything outside of the building. So that might be another advantage. A real disadvantage, though, is you've got to hire an electrician. With the standard installation, you know, each of us could come in here and hook up a load side connection, because all you have to do is just turn off your main breaker, pop a breaker in, hook it up, you're ready to go. The only thing that would prevent you is sometimes local ordinances or codes say that a licensed electrician has to make that final connection. In those cases, usually the installer goes ahead and hooks it up, just doesn't turn on the breaker. And then the electrician comes out, charges a few $100 and turns the breaker on. You know, it's a silly rule, but that's how they do it. You know, we did an installation in Minnesota where they required that a master electrician be on site. We couldn't find any that knew anything about solar. So the guy just sat in his car and slept, you know, but he charged us for the job. So anyway, those are the rules of government requirements.
But, and if you want to supply more power than the 20% of your box, you could do
Yes.
it this way.
Yes, that's true. Yeah, so if, let's say we had 60 amps coming in, well, we'd have to do a supply side connection. We couldn't do a load side connection with 200 amp box. Now there is a workaround on that, and I have had it approved by some inspectors where you just put in a smaller main breaker. You know, let's say you had a 200 amp box with a 200 amp service from the utility, but I want to come in with 60 amps. Well, I could come in here and take this main breaker out and replace it with a 175 amp main disconnect. I still have 200 amps available from the utility, but I'm only going to use 175 of them. So in combination, 60 amps plus 175 amps is still less than 120% of the rating of the box. So that's another option as well. But sometimes your inspectors are going to balk at that. I don't know why they would, but they do. You know, it's just because they've never seen it happen. And anything that's unusual, they don't like. Okay. All right, any other questions from this jumble of mess that we've got here? Okay, so hopefully you find that a little bit helpful, going through a full example like that. And do some practice problems. Just try and get these things, work through all the examples. And if you do run into any problems, send me an email. I'll answer your question. Other than that, we'll see you guys on Tuesday. Okay.
Thank you.
Sure.
Bye-bye.
Jay.